and welcome. Let's go ahead and differentiate or integrate this excuse me. Welcome. In this video, I'm going to show you how to differentiate or integrate our key power series in order to express inverse tangent of x as a power series. And of course, we're going to look into its interval and radius of convergence. Okay, so there are a couple things we have to recall, and I'm giving the warning to those of you who have been watching my videos that you might want to skip ahead a few seconds because I'm going to recall that key power series. Although I will add, if you are in my class and haven't memorized this yet, then just keep watching the videos. Try to see if you can remember the key power series, pause the video, then, unpause it and see if you got it. So the sum from 0 to infinity of x to the n, that's 1 plus x squared plus x cubed. And it goes on, and what makes it so key is that as long as x and its absolute value is less than 1, then this adds up to 1 over 1 minus x. Okay, so that's the first thing I want you to recall. The second thing I want you to recall is that the derivative of tangent inverse x is equal to 1 over 1 plus x squared. Now, this video, those of you in my class have already seen it. If not, you should see a card popping up somewhere up here saying a recommended video to watch. And that'll show you what this is the power series is. So in this video, what we're going to do is we know that if we integrate this, we'll get arctangent of x. So I know tangent inverse of x is equal to the integral of 1 over 1 plus x squared dx. All right, now that we have recalled the first and the second thing, I'm going to rewrite this as the power series that we have already found. And so hopefully you've seen that card pop up. I don't remember how many times I've mentioned it by now. If not, it should be up here soon. So this integral, or excuse me, this as a power series is going to be 1 minus x squared plus x to the fourth minus x to the sixth plus x to the eighth, and so on. Integrating term by term, I get x minus x cubed over 3 plus x to the fifth over 5 minus x to the seventh over 7, and you get the gist. Let's go ahead and find a pattern. This is the sum from n, and I'll wait to see here what works. Now, I want odd numbers. Odd numbers can be expressed as 2n plus 1, where even are just 2n. So I'm going to start at 0 to guarantee that I'll end up with a 1 when I put a 0 here, 2 times 0. So this is 2n plus 1 times negative 1. Our first term we want to be positive, so I'll just leave this to the nth power, divided by 2n plus 1. So to rewrite it in a neater manner, this is the sum from n equals 0 to infinity of negative 1 to the nth power times x to the 2n plus 1 power over 2n plus 1. So I'm going to look at the ratio test here. Recall, the ratio test asks us to look at the limit of the ratio between the next term and the previous term and ensure that's less than 1. Well, in this case, this is the limit as n approaches infinity of x to the 2n plus 1 over 2n plus 1. Excuse me, that's not an exponent. And then dividing by a fraction, it's like multiplying by the reciprocal, so I'll have 2n plus 1 here over x to the 2n plus 1. And that's because in this case, my a sub n term was x to the 2n plus 1 over 2n plus 1. And the n plus 1 term is just adding 1 to each of these n's. And 2n plus 1 is just 2n plus 2 plus 1, or 2n plus 3. So this is the limit as n approaches infinity of x squared times 2n plus 1 over 2n plus 3. Okay, well, how do we evaluate this limit? Well, it's concerned with n, so this can just come out to the front here. And this is the limit as n approaches infinity of 2 plus 1 over n over 2 plus 3 over n. So this is just x squared, since this whole limit's going to be just 1. And so long as that's less than 1, our series converges. And this occurs if and only if x is between -1 and 1. So all that's left to do is check the endpoints. When x equals -1, what does this series become? Oops. And when I say this series, I mean this right here. We're replacing our x's with -1 and then 1. So -1 to the n times -1 to the 2n plus 1 over 2n plus 1. This is the sum from n equals 0 to infinity of -1 to the 3n plus 1 over n, 2n plus 1. And this is going to converge with the comparison test to the. Now this infinite series converges by the alternating series test. Okay, so I can include an underline here. Those of you in my class, I'm going to want to see the test here, but we've already covered these in depth, so I'm not going to cover the alternating series test here, but I will expect to see the alternating series test covered. Okay, so now let's look at the other case. Let's look at the case when x equals 1, we have the sum from n equals 0 to infinity of -1 times 1 to the 2n plus 1. I forgot my n here. So this is the sum from n equals 0 to infinity of -1 over 2n plus 1. And of course, this is to the end. And again, this one also converges by the alternating series test. Okay, so our interval of convergence is between, that is the absolute value of x is less than or equal to 1, and our radius of convergence is just 1. All right, keep calm and math on. You got this.